Okay, welcome. So what I decided to do for my students was just kind of create a little bit of a document to help prepare them for pre-calculus. So the first installment for preparing for pre-calculus was just some algebraic and arithmetic operations. And this is pretty basic, like pre-algebra 1 kind of stuff, but a lot of things that students, that we come across pre-calculus that sometimes I have to, reteach students. So I thought it'd be a good idea just to kind of go over them. So, the first one is dealing with fractions. A lot of times students will see fractions and they're like, I don't remember this, it's been so long and stuff like that. So we kind of like to go through, fractions again one more time for them. So first of all, when we're looking into combining fractions here, I have 1/4 plus 1/3. Remember the main idea of when you're adding or subtracting fractions, you got to get a common denominator. And since 4 and 3 are not the same, we got to be able to identify what is the common multiple of both 3 and 4. And you could list out your multiples, but hopefully at this stage in the game, you can recognize that the LCD in this case is going to be equal to 12. So therefore, what I need to do is I need to get both of these denominators to be 12. So I'm going to multiply here by 4. Now again, to keep the fraction what we call an equivalent fraction, you got to make sure you multiply the top and the bottom by 4. Otherwise, you're changing the value of the fraction. And on the left side, I'm going to multiply by 3/3. So by doing that, now what I obtain is 3/12 plus 4/12. And now what you can see is now we can add them because they have common denominators. So 3/12 plus 4/12 is just going to be 7/12. Now, the next one usually gets confused with a lot of students because we're having a fraction minus a whole number. And it's like, what do we do here? Like, what do we do? Well, again, if we're combining fractions, we want the fractions to both have, or we want to, combine fractions. So what we're going to do is we're going to change our whole number to a fraction just by putting it over 1. So now what we're looking for is what is the LCD of 3 and 1? Well, the smallest multiple that 3 and 1 both divide into, in this case, is just going to be 1. Or I'm sorry, LCD here is 3. So all I need to do over here is just multiply by 3/3. Therefore, I have 2/3 minus 12/3. And then 2 minus 12 is going to be 10/3. Now, this is an improper fraction, and that's perfectly fine. I tell my students I like to leave answers in improper fractions. I do not want to leave this as a decimal, nor do I want to leave this as a mixed number. So usually improper fractions are the most accurate and the way that I prefer to have my students do this, or leave their answers. For the next example here is another fraction, and you can see in this case we are taking a fraction and dividing it by another fraction. And this one comes up quite a bit. And one of the things is by the end of the year, students are like, all right, I get you on this one. Like, I remember what to do. They basically can recite everything. So if we basically, we don't want a fraction and you can see here we have 3 fractions: fraction numerator, fraction denominator, and then another big fraction bar. So what we want to do here is we want to get rid of this fraction in the denominator. Not really get rid of it, but what we want to do is we want to get it to be 1. So what number multiplied by 3/4 is going to make that 1? Well, that is going to be its reciprocal. So all we're going to do is multiply by 4/3. Well, again, just like we did for the LCD, what do you do on one side, you have to do, or whatever you do in the denominator, you have to do in the numerator. And that's why we sometimes say, oh, just flip and multiply, because what happens here is when I multiply 3/4 times 4/3, that becomes 12/12, which is really just 1. So then what I have here is 8/15 over 1. Well, I don't really need to write that 8/15 over 1. I can just rewrite, I can just keep it as 8/15. Now, in this example, again, we can simplify this. No, we can't simplify this. We're going to leave that just as it is. I chose the problem that you couldn't be simplified. So my final answer I'll just write as 8/15. Okay? For the next example here, we have 2/5 times 9/2. Now, a lot of times students will get into this and they go to the cross multiplication, which I absolutely hate. So please make sure you do not apply cross multiplication, or even just remove cross multiplication from your memory. That's probably even better. But I decided on this example because one thing that we notice is, when you multiply fractions, you can multiply directly across 8/10. But you realize here we need to simplify this. So we can divide the top and the bottom. They both have a common denominator, or a common factor of 2. So if you divide the top and the bottom by 2, you get 9/5. Okay? Well, another way to look at this is simplifying fractions before we apply our operations. And what you notice is, since these fractions are separated by multiplication, I can take 2 divided by 2 and divide that out, and therefore I'm just left with a 9/5. So you can go through the process, but always look to be simplifying your radicals first, or simplifying your fractions first. All right, moving on to simplifying radicals. So when simplifying radicals, what we're going to want to do is, again, what the square root symbol is saying is the square root of what number, equals square root of, what is the square root of 16? Which is basically saying what number multiplied by itself is going to equal 16. So, the main important thing is you really should know your square numbers. For instance, 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. Okay, so obviously we see that 4 squared is 16, so the square root of 16 is just going to equal 4. Now, in this example, you could use prime factorization, but that was kind of like an algebra technique or even pre-algebra technique. So the main important thing that I want to do is I want to use the properties of radicals to, simplify this. And what we can do is I can simplify the square root of 8 into the square root of 4 times 2. Right? So all I'm doing is breaking up 8 into square root of 4 times 2. Now, the important thing is you want to break it up as long as it can be a product of a square number. And you can see here that 4 is a square number. And I can take, now what I can do is I can break this up into the square root of 4 times the square root of 2. Because if you multiply two radicals in your numbers, as long as they have the same index, you could just multiply square root of 4 times square root of 2 would equal square root of 8. But now I can take the square root of 4, which is 2, and that's going to be times the square root of 2. Okay, and then in this last example here, I have the square root of 20. And again, we're going to kind of do the same thing. Now, the important thing is where students, sometimes will get mixed up and say, oh, well, that's going to be, 10 times 2. Well, the problem is 10 and 2 are not square numbers. So that's not going to be my best way to be able to simplify this radical. However, I could break this up into square root of 4 times 2. I'm sorry, not square root of 4 times 2, square root of 4 times 5. Now, breaking up this way, again, you could see we're going to follow the same process. So that's going to be 2 square root of 5. And last but not least, a complex number. If you haven't discussed complex numbers, I apologize. I'm just going to do a rough little sketch because we will get into complex numbers. But the main important thing is just remember that I represents your imaginary unit, which is basically the square root of -1. So that is, square root of -1 is not in our real imaginary system or our real number system. So we use I to represent it and the imaginary or complex unit system. So whenever you're taking the even root, in this case the square root of a negative number, we're going to need to use this imaginary unit. So what I'm going to do is, again, I'm going to break it up in a square number. So I'm thinking, all right, what number multiplied by 32? Well, you could do 4 and 8, right? But then, see, the problem with using 4 and 8 is you could do 4, which is square root of 2, but then you're going to have 8, which you're going to have to break down again. So your idea is, what is the largest square number that I can divide into 32? And that answer is 16. So what I'm going to do is I'm going to break this up into -1 times 16 times 2. Now, I know that the square root of -1 is I, square root of 16 is 4, and then the square root of 2 is, can't take the square root of 2, so we can just leave it just like that. Now, usually we don't want to write this as I4, just like I is, even though I is not a variable, we like to write it after our number, so we'd write this as 4i times the square root of 2. Now, you could also write the I at the end, 4 square root of 2. But if you write it like this, it's going to look like it's under the radical, right? And we don't want the I to be under the radical. So a lot of times what I'll do is I'll just add a little close bar on my radicals and then put the I right there. All right? And I think that's pretty good. I'll just kind of deal with that. Take a look at that as far as my first video to kind of see, how that looks or how that kind of works. All right, thanks. Oh, okay, how that works. Haha, my options are right here, which I can just do.